Welcome. This video explains the 5G PDU Session Establishment procedure for a user equipment that is RM registered and CM connected. We'll break down each step and explore the roles of key network functions. A PDU session, or Protocol Data Unit session, is a logical connection between the user equipment and a data network, such as the Internet. This connection enables data transfer and is fundamental to 5G communication. Here we see the basic concept. The user equipment on the left establishes a PDU session with a data network on the right. This logical connection allows data to flow between the device and external networks like the Internet. For this procedure, the user equipment must be in two specific states. First, RM registered means the UE is registered with the network. Second, CM connected means there's an active signaling connection between the UE and the network. Throughout this video series, we'll examine the complete step-by-step establishment procedure, understand the roles of key network functions like AMF, SMF, UPF, UDM, and PCF, explore how these functions interact, and discuss recent developments in 5G technology. Now that we understand the basics, let's dive into the detailed procedure and explore how 5G networks establish these critical data sessions. Before a UE can establish a PDU session, it must be in two specific states: RM registered and CM connected. These are fundamental prerequisites that define the UE's relationship with the 5G network. Let's visualize the key network elements involved. We have the UE, or user equipment, the RAN, or radio access network, and the AMF, or access and mobility management function. First, RM registered state means the UE is registered with the 5G network. The AMF maintains location information for the UE, enabling the network to reach the device when needed. Now let's examine the second required state, CM connected. CM connected state means the UE has an active signaling connection with the AMF. This involves an RRC connection between the UE and RAN, and an NGAP association between the RAN and AMF. Both states must be active simultaneously. The UE must be registered and have an active connection before it can request a PDU session. The PDU Session Establishment process begins when the user equipment, or UE, needs to establish a data connection with the 5G network. The UE initiates this process by sending a PDU Session Establishment request message directly to the Access and Mobility Management function, or AMF. This request message contains three critical pieces of information that help the network understand what type of connection the UE needs and how to route the data properly. First, the service type indicates what kind of service the UE is requesting. This could be standard Internet access, specialized IoT connectivity, or emergency services. Second, the data network name, or DNN, tells the network which external data network the UE wants to connect to. This could be the public Internet or a specific private network. Third, the Single Network Slice Selection Assistance Information, or SNSI, specifies which network slice should handle this session. Network slicing allows operators to create dedicated virtual networks optimized for different types of services. With this comprehensive request message, the UE provides the AMF with all the necessary information to begin the PDU session establishment process and route the request to the appropriate network functions. The AMF receives the PDU session establishment request and must now select the appropriate SMF to handle the session management. This selection is a critical decision that affects the entire session. The AMF uses several key criteria to make this selection decision. These include the SI, which identifies the network slice, the DNN, or data network name, the UE's subscription data, and current network policies. The AMF may consult the Network Repository Function, or NRF, to discover which SMFs are currently available in the network. The NRF acts as a service discovery mechanism, providing information about network function instances and their capabilities. Based on the criteria and NRF information, the AMF sees multiple SMF options. Each SMF may serve different network slices, have different capabilities, or be located in different network positions, such as edge locations. The AMF analyzes all the criteria and makes its selection. In this case, it chooses SMF1, which best matches the requested SNSA and DNN parameters. This selected SMF will now be responsible for managing the PDU session. This SMF selection process ensures that the most appropriate session management function handles the PDU session based on the specific requirements and network conditions. The AMF will now forward the session establishment request to the selected SMF. The AMF now forwards the PDU session establishment request to the chosen SMF. This is a critical handoff where the session management responsibility transfers from the AMF to the SMF. The request travels from the AMF to the SMF through the service-based interface. The SMF is specifically designed to handle session management functions in the 5G core network. Upon receiving the request, the SMF immediately begins creating a session management context. This context is like a digital blueprint that will govern the entire PDU session. This session management context serves as the foundation for all subsequent session operations. It contains essential information about the user, the requested service, and the network resources that will be needed. With the session management context established, the SMF is now ready to coordinate with other network functions to complete the PDU session setup. This context will guide every decision the SMF makes throughout the session lifecycle. The SMF now needs to verify that the user is authorized to establish the requested PDU session. To do this, it communicates with the UDM. The UDM, or Unified Data Management Function, is the central repository for all subscriber information in the 5G core network. It stores user profiles, subscription data, and authentication credentials. The SMF sends a request to the UDM to retrieve the subscriber's profile and authentication information for this specific user. The UDM retrieves three key pieces of information: the user's profile containing service permissions, authentication data for security verification, and subscription information, including allowed services and network slices. The UDM sends this subscriber information back to the SMF, enabling the SMF to verify that the user is authorized to establish the requested PDU session with the specified quality of service and network slice. With the subscriber data now available, the SMF can proceed with confidence that the user is properly authenticated and authorized for the requested PDU session. The SMF UDM interaction is now complete, and the session establishment process can continue to the next step. The SMF now needs to obtain policy rules for the PDU session. It initiates communication with the PCF, the policy control function, which is responsible for providing network policies. The SMF sends a policy request to the PCF, asking for the specific rules that will govern this PDU session. This communication is essential for ensuring proper session management. The PCF responds with comprehensive policy rules that include two main categories: quality of service parameters and charging policies. The first category is quality of service parameters. These rules define how the network should handle traffic for this session, including bandwidth allocation, latency requirements, packet loss tolerance, and priority levels. The second category covers charging policies. These rules determine how the session will be billed, including data usage tracking, billing rates, usage quotas, and specific triggers that initiate charging events. These policy rules are crucial because they dictate exactly how the SMF will manage the PDU session throughout its lifetime, ensuring both quality of service and proper billing. With these policy rules in hand, the SMF can now properly manage the session by prioritizing traffic according to QoS requirements, allocating resources based on policies, controlling charging and billing in real time, and enforcing the appropriate service levels. The session management function must now select the appropriate user plane function to handle data traffic for this PDU session. This selection is critical for ensuring optimal data routing and network performance. The SMF acts as the intelligent decision maker, responsible for selecting one or more user plane functions based on various network criteria and requirements. Multiple UPF candidates are available in the network, each with different characteristics. UPF-A offers edge location with low latency, UPF-B provides high capacity from a central location, and UPF-C offers balanced performance from a regional position. The SMF evaluates multiple criteria when selecting a UPF. These include network topology, UE location, quality of service requirements, current load balancing needs, and the specific type of service being requested. The SMF analyzes each available UPF against these criteria, evaluating which option best meets the requirements for this specific PDU session. Based on the evaluation, the SMF selects UPF-A due to its edge location and low latency characteristics. which best match the requirements for this PDU session. Once selected, the UPF becomes responsible for routing and forwarding all data packets for this PDU session, ensuring efficient data delivery between the user equipment and external data networks. The selected UPF now handles all data routing between the user equipment and external data networks, forwarding packets efficiently based on the established session parameters. UPF selection is now complete. The SMF has successfully chosen the optimal user plane function, and the data routing path is established for efficient packet forwarding throughout the PDU session. The SMF now configures the selected UPFs with all necessary session parameters. This critical step establishes the data forwarding infrastructure for the PDU session. The SMF communicates with each UPF using the PFCP protocol over the N4 interface. This standardized interface ensures reliable configuration delivery between session management and user plane functions. The SMF sends detailed configuration messages containing forwarding rules that define how packets should be routed, quality of service parameters for traffic prioritization, and session-specific information for proper data handling. The configuration includes three main components: forwarding rules that determine packet routing paths, quality of service parameters that ensure proper traffic handling, and session-specific information that maintains connection state. Once configured, each UPF acknowledges successful setup and becomes ready to handle user plane traffic according to the established parameters. The data forwarding infrastructure is now fully prepared for the PDU session. The Session Management Function, or SMF, now needs to ensure that the radio interface can support the quality of service requirements for the PDU session. This involves coordinating with the Access and Mobility Management function to allocate radio resources. First, the SMF analyzes the quality of service requirements for the PDU session. These include bandwidth allocation, latency constraints, and reliability parameters that must be maintained over the radio interface. The SMF then communicates these quality of service requirements to the AMF, requesting that appropriate radio resources be allocated to support the PDU session. The AMF receives this request and triggers the radio access network to allocate the necessary resources. This ensures that the radio interface can meet the session's quality of service requirements. Finally, the RAN establishes a radio bearer between itself and the user equipment. This radio bearer is configured with the specific quality of service parameters needed for the PDU session, ensuring optimal data transmission over the wireless interface. This radio resource allocation step is crucial for maintaining end-to-end quality of service. It ensures that the wireless link between the user equipment and the radio access network can support the data rates, latency, and reliability requirements of the PDU session. The Session Management function now sends the PDU Session Establishment Accept message back to the user equipment. This critical message travels through the Access and Mobility Management function and contains all the essential session parameters. The accept message contains the assigned IP address that the user equipment will use for data communication, along with the PDU session identifier and quality of service parameters that define how the session will operate. The message flow begins at the Session Management function, travels through the Access and Mobility Management function, and finally reaches the user equipment, confirming that the PDU session has been successfully established. With the PDU Session Establishment Accept message received, the user equipment now has everything needed to begin data communication. The session is officially established and ready for data transfer. With the PDU session now fully established, the critical moment arrives. Data transfer can begin. All the previous signaling and setup steps have created a complete data path from the user equipment to external networks. The established PDU session creates a logical data path connecting the user equipment through the radio access network, with the user plane function serving as the central routing hub for all user data. The user plane function plays the crucial role of packet routing and forwarding. It receives user data from the radio access network and intelligently routes it to the appropriate external data networks, whether that's the internet, private networks, or cloud services. Data transfer is bidirectional. When the user equipment sends data, packets flow from the UE through the RAN to the UPF, which then forwards them to the destination data network. Similarly, When data networks send information back to the user, the UPF receives these packets and routes them back through the RAN to reach the user equipment, completing the bidirectional communication path. The user plane function provides several critical capabilities during data transfer. It performs packet routing and forwarding, enforces quality of service policies established during session setup, monitors traffic for billing and analytics, and serves as the interface point to external data networks. Data transfer has successfully begun. The PDU session is now fully operational, enabling seamless bidirectional communication between the user equipment and external data networks through the optimized routing capabilities of the user plane function. The user equipment, or UE, plays the crucial initiating role in PDU session establishment. As the starting point of the entire process, the UE has several key responsibilities. First and most importantly, the UE initiates the PDU session establishment by sending a request to the network. This request includes critical information such as the data network name, or DNN, and the single network slice selection assistance information, known as SNSSI. The UE also specifies the required service type in its request, helping the network understand what kind of connectivity and quality of service is needed. Once the network processes this request, the UE receives the session parameters and can begin data communication. In summary, the UE serves as both the initiator and the endpoint of the PDU session establishment process, driving the entire procedure from start to finish and enabling seamless data connectivity in the 5G network. The RAN, or Radio Access Network, serves as the critical bridge between user equipment and the 5G core network during PDU session establishment. The RAN's primary responsibility is providing radio connectivity. It establishes and maintains the wireless link that allows the UE to communicate with the network infrastructure. When a UE initiates a PDU session establishment request, the RAN acts as a transparent forwarder, relaying this signaling message to the appropriate core network functions. The RAN performs two essential functions. First, it provides the radio interface and manages radio resources. And second, it forwards signaling messages between the UE and core network functions like the AMF. During the PDU session establishment procedure, the RAN ensures reliable radio communication while seamlessly passing control plane messages between the user equipment and the core network, enabling successful session setup. The Access and Mobility Management Function, or AMF, serves as a critical control hub in the 5G core network with three primary responsibilities. First, the AMF handles SMF selection. When a UE requests a PDU session, the AMF must choose the most appropriate session management function based on network slice, data network name, and operator policies. Second, the AMF manages mobility. As users move throughout the network coverage area, the AMF tracks their location, handles handovers between base stations, and ensures continuous connectivity. Third, the AMF acts as a signaling relay, forwarding messages between the UE and the SMF. All session management messages pass through the AMF, which ensures proper routing and security. The AMF is essential for 5G network operation, serving as the central coordination point for session establishment, user mobility, and secure message routing throughout the core network. The Session Management Function, or SMF, is the central orchestrator of PDU sessions in the 5G core network. It manages the entire lifecycle of user sessions and coordinates with multiple network functions. The SMF has four core responsibilities in PDU session establishment. First, it manages the complete session lifecycle from creation to termination. Second, it allocates network resources and manages quality of service parameters for each session. Third, it enforces network policies received from the policy control function to ensure proper service delivery. Fourth, it assigns IP addresses to user equipment and manages network connectivity parameters. The SMF interacts with three key network functions during PDU session establishment. Let's examine these critical interactions. The SMF retrieves subscriber information and authentication data from the Unified Data Management function. It obtains policy rules and quality of service parameters from the policy control function. Most importantly, the SMF selects and configures user plane functions to handle the actual data traffic for the session. The SMF manages the complete PDU session lifecycle through three main phases: establishment, modification, and release. During establishment, the SMF coordinates with network functions to create new sessions. During modification, the SMF coordinates with network functions to update existing sessions. During release, the SMF coordinates with network functions to terminate sessions and free resources. Through these comprehensive capabilities, the SMF ensures reliable and efficient session management, making it a critical component in the 5G core network architecture. The user plane function, or UPF, is the data processing powerhouse of the 5G core network. It handles all user plane traffic and serves as the critical bridge between mobile devices and external data networks. The UPF's primary responsibility is handling user plane traffic. It receives data packets from mobile devices through the radio access network, processes them according to network policies, and forwards them to their destinations. The UPF enforces quality of service policies to ensure different types of traffic receive appropriate treatment. High-priority traffic, like emergency calls, gets processed first, while lower-priority data is handled accordingly. The UPF serves as the gateway between the 5G core network and external data networks. It connects mobile devices to the internet, private corporate networks, and other data services, enabling seamless data communication. In summary, the UPF is the critical data processing hub of the 5G core network. It handles user plane traffic routing, enforces quality of service policies, and provides the essential connection between mobile devices and external data networks, making it indispensable for 5G data services. The UDM, or Unified Data Management function, serves as the central repository for all subscriber information in the 5G core network. The UDM stores critical subscriber information, including user profiles, authentication keys, subscription data, and security credentials. This data is essential for network access and service authorization. During PDU Session Establishment, the SMF communicates with the UDM to retrieve the subscriber's profile and authentication information needed for session authorization. The UDM responds by providing the requested subscriber information back to the SMF, enabling proper authentication and authorization for the PDU session. The UDM is functionally similar to the HSS in previous generation networks, but enhanced for the service-based architecture of 5G core networks. By centralizing subscriber data management, the UDM ensures consistent and secure access to user information across all network functions in the 5G core. The Policy Control Function, or PCF, serves as the intelligent policy engine within the 5G core network. It plays a crucial role in controlling how network resources are allocated and managed. The PCF creates and manages policy rules that govern network behavior. These rules define how quality of service should be applied and how charging should be controlled for different services and users. During PDU Session Establishment, the PCF communicates directly with the Session Management function. It provides the SMF with specific policy rules that will govern the session's behavior. The PCF controls two critical aspects of network operation. First, quality of service control, which determines bandwidth allocation, latency requirements, and priority levels for different types of traffic. Second, charging control, where the PCF defines how network usage should be measured, billed, and monitored. This includes data volume limits, time-based charging, and service-specific billing rules. The PCF is equivalent to the policy and charging rules function from 4G networks, but with enhanced capabilities for 5G's advanced services. It ensures that network resources are used efficiently while maintaining proper billing and quality standards. Multi-access PDU sessions represent a significant advancement in 5G technology, introduced by 3GPP to enhance connectivity flexibility and reliability. Traditionally, a UE establishes a PDU session through a single access network, typically a 3GPP network like 5G or LTE. Multi-access PDU sessions allow a single UE to simultaneously connect to multiple access networks. This includes both 3GPP networks like 5G and LTE, as well as non-3GPP networks such as Wi-Fi. The key innovation is that both connections serve the same PDU session simultaneously, creating redundancy and allowing for seamless handovers between access technologies. Both access networks contribute to the same PDU session, providing enhanced reliability and performance through path diversity. Multi-access PDU sessions provide several key benefits: enhanced connectivity through multiple paths, improved reliability with redundant connections, seamless handovers between access technologies, and better load balancing across available networks. This advancement represents a significant step toward more flexible and resilient 5G connectivity, enabling applications that require high availability and performance. A significant recent development in 5G is the enhancement of UE route selection policy reporting, known as URSP reporting. This advancement enables more intelligent and adaptive network management. URSP rules define how a UE should select routes and access networks for different types of traffic. These policies guide the device in choosing between Wi-Fi, 5G, or other available networks based on application requirements. Previously, these URSP rules were static policies. The UE would follow them, but the network had limited visibility into how effectively these rules were being enforced or whether they needed adjustment. The new URSP reporting capability allows UEs to actively report back to the SMF about how URSP rules are being enforced. This includes information about which rules are being used, their effectiveness, and any challenges encountered. This creates a dynamic feedback loop. First, the UE reports on how URSP rules are being enforced in real-world conditions. The SMF then analyzes this performance data to identify optimization opportunities. Finally, the SMF can update and refine URSP policies based on actual usage patterns and performance metrics. This enables real-time network optimization, improved user experience, and truly adaptive policy management that responds to changing network conditions. URSP reporting represents a shift from static, predefined policies to dynamic, data-driven network management. This enhancement allows 5G networks to continuously learn and adapt, providing more responsive and efficient connectivity for users. Edge computing represents a fundamental shift in 5G network architecture. Instead of centralizing all user plane functions in distant data centers, edge computing brings UPFs closer to users at the network edge. Traditional 5G deployments place UPFs in centralized locations, often hundreds of kilometers away from users. This creates significant latency, as data must travel long distances through the network. Edge computing transforms this architecture by deploying UPFs at the network edge, much closer to users. This dramatically reduces the distance data must travel, cutting latency by up to 80%. This dramatic latency reduction enables revolutionary applications that were impossible with traditional architectures. Augmented and virtual reality applications require ultra-low latency to prevent motion sickness and provide immersive experiences. Autonomous driving represents another critical application. Self-driving vehicles need to process sensor data and make split-second decisions. Edge computing enables real-time vehicle-to-everything communication with latencies under 5 milliseconds. Edge computing also delivers significant performance improvements beyond latency. By processing data locally, edge UPFs reduce bandwidth consumption on backhaul networks and improve overall network efficiency by up to 40%. Edge computing represents the future of 5G networks, enabling applications that demand ultra-low latency and high performance. As more UPFs are deployed at the network edge, we can expect to see revolutionary new services that were previously impossible with traditional centralized architectures. That concludes our comprehensive walkthrough of the 5G PDU Session Establishment procedure. We've covered every step from the initial request to successful data transfer. Let's visualize the complete flow one final time. The procedure involves 7 key network functions working together in perfect coordination. The procedure flows from UE request through RAN to AMF, then SMF coordinates with UDM for subscriber data, PCF for policies, and UPF for user plane setup, finally enabling data transfer to external networks. Understanding these steps and the roles of each network function is absolutely crucial for grasping the fundamentals of 5G network architecture and session management. This knowledge forms the foundation for understanding advanced 5G concepts like network slicing, edge computing, and multi-access scenarios. Thank you for watching this comprehensive guide to 5G PDU Session Establishment.